I will show you the example of it, and it will be more clear how to perform those steps for the logarithmic differentiation. So the whole cool point is there's some kind of function which you don't like to work with, usually because it has powers. You apply log to both sides. So log became such an awesome function that it's used to solve stuff. Equations, differential equations, graphing, fast processes being slowed down. Log is a function that people actually like to use to apply to something. So people usually don't do, oh, let's do sine from the left and right. Oh, let's do arcsecant on the left and the right. No, but with log they do. So log became very awesome at some point. Then you use laws of logs to make whatever you have look easier. That's the whole point. Why you're applying it, to use laws of logs. Or sometimes you use definition. You remember definition. So if you have, let me remind you definition here. If you have log base a of x equals to y, then you can write down e, no, that's not e. Base is the same, a, and now input becomes output, output becomes input. Y equals x. That's the definition. So you can use that also. And then you perform implicit differentiation. As you can see, it's everywhere. Related rates. In general, like I'm trying to explain to students that in general, in real life applications of a rocket flying, bacteria division, waves in the ocean, there's lots of cool equations on the traffic equations. You don't have the stuff equal y equals blah, 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 and then you find how fast the waves are moving. Yeah, that's too easy. That's the thing. We teach you the simple stuff first. Derivatives. Was derivative of sine and so on. But in general, it's always scattered around equations. The functions are scattered around. So implicit differentiation is used more often than you think. Because you need to know that you just drop differentiation bomb on everything and differentiate everything massively. So you differentiate both sides. Left-hand side becomes y prime over y. I will tell you in a second why. Solve for y. Plug it from the very beginning, and you're good to go. So in the future, we're gonna have extra step after that. Extra step. Well, it's fine. So also, you need to check the domain, I guess, sometimes, but that's mostly for the logs and x equations. Example. So I posted all those notes. Don't be afraid if you did not copy this, because I have all the notes posted, as always, very organized, very organized. In general, my Canvas, one of the best organized works on the department, and I'm very proud about it because it took me time to organize Canvas nicely. So right now we have B section started. I have 3 classes added to my B section, which is 375 students total, because each class is 125, and they all in one Canvas shell. In one. So this Canvas shell better be good. You know, if there's 375 people relying on this Canvas shell, it's better be good. So my Canvas shells are very...
Is it an online course? Or
online. Yeah. And they all get...
offline for A and B session?
No, it's online only, A and B. And all they're scattered around the world, not only around America, but some of them are serving in Hawaii and so on. Some of them are on the ship right now because they're also serving in Navy and so on. It's a very interesting experience. Here is the very cool idea. What is the function x to the x and how to work with this function? X to the x function doesn't have a name. So note, very interesting idea. You will be, I think, impressed right now, at least by this. X to the n, that's polynomial. And we know that we use power rule when we differentiate polynomial. N goes down, x to the n minus 1. Now, n to the x, or a to the x, right? Let's put a. That's exponential. And we know that a to the x prime is a to the x, and also times natural log of the base. But this one is x to the x. It's both at the same time. So what we're gonna do? Well, there's actually no rule how to differentiate x to the x function. And x to the x function actually is the fastest one. It's faster than exponential. Obviously, at infinity, a to the a million is a huge number. But what if it's a million to the million? Can you imagine? So x to the x grows really fast. It's faster than a factorial function and so on. But you cannot use power rule or e to the x rule for this case. It's both and neither. at the same time. So we're going to perform this idea to get rid of the situation of x to the x. And it doesn't have to be x to the x. Sine x to the, x squared is the same problem. Ln x to the, whatever, cosine x. It's the same form of a function. Can someone tell me why? Like stare at those three functions, x to the x, sine x to the x squared, ln x to the cosine. What is similar between those three? Can you notice? Oh, someone at the end. Yes? Yeah. Yes. And since people in front did not hear you, anyone in front? Yes. Wait. You haven't. Yes.
There's x in the base and the power as well. So there's a function, the base function.
Yeah, very amazing. Both things are amazing. I like it. People cannot hear you anyway, so it's good. So there's what they both said. X is in the base and x in an exponent. Function in the base and function to the exponent. That never happened before. We did not have this example before. And that's a pretty common example, actually. So it's input to the input. That's how I would call it. Input to the input. And then the way you guys said is actually better. It's more professional to say it. It's a function raised to the function. I like the input to the input case because it's kind of more visual. But in general, yes, it's function to the function. So base is changing. Then it's polynomial. Exponent is changing. Then it's exponential. And this one is both. Well, you must use logarithmic differentiation. Differentiation. Recently, I like messing up English. I don't know why. It's just a new thing now. I'm doing that now. So, logarithmic differentiation means step 1. Before differentiating, apply log to both sides and make it happen. Make it better. Make the function great again. Anyway, solution. Y equals x to the x. Ln on the left, Ln to the right. Okay, you can do log 5 if you want. You can do log, but why would you do that? Use Ln, that makes sense. So it's not a requirement not to use anything but Ln. But step 1, if you see my steps, step 1 says apply log, any kind of log you want to both sides. And it makes sense to apply Ln because it's everywhere. It's natural to apply natural logarithm. So the left-hand side becomes, and you use properties. Step 2, you use properties. Use definition or properties. Oh, let's not call it, actually properties too long to write. And actually it's called laws of logs. Laws of logs. Laws of logs tells us that, okay, left-hand side is still ln y. But the right-hand side now is ln x to the x. Now let's review what it means to have ln x to the x. For now, for the first thing I will tell you is it's important to understand parentheses here. People who have bad relationship with parentheses will struggle more and more in calculus sequence and in physics and in chemistry. Parentheses change everything, especially when we're going to have derivatives with 5 variables. dx, dy, dz, dt, dm at the same time. Parentheses will tell you what we're working with. So let me make a note. We made this note last week, but I can repeat it as many times as needed. ln x to the x, where it's an input, is not the same versus ln x to the x. Do you see that? One is ln of x times x times x, blah, 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 versus. And another one is, guess what? ln x times ln x times ln x. That's the difference. So not only that is important, but also properties are important. So property for the exponent inside of the log works only on the input. So I want to use laws of log that says ln x to the a equals a ln x. This only works when a is on top of the input. So it only works in the first situation, not the second one. To remember this, if you think it's hard to remember, then remember log works with inputs and it's doing magic with inputs. But log times log times log has no formula for that. So log is good with inputs. Thus, I can take this x and put it down. And by putting it down, I mean multiply. Putting it down. It will be ln y equals x times ln x. And I'll put parentheses for you everywhere. Like so. And that's basically why we did it. We had x input to the input case, now we don't. We have input times input. And guess how you differentiate input times input? You do product rule. So we know that. We basically took the situation we don't know and fixed it. We changed it, transformed it into a situation we know. And that's what science is about. You will be left by yourself when you're hired by a company to figure out things like this. That's what you paid for. To figure out things which are new using tools you know. And that's the idea. But does it make sense what I just did? Log and then x goes down multiplied using properties. And I put this here so you have a memory, good memory. I'm using the laws of logs, specifically this one with power. Okay, step 3, you start implicit differentiation. Implicit differentiation. Oh, did I ever mention what's the goal? What is the goal of all of this? I think I forgot to mention. We're working with x to the x. Find y prime. So the whole goal is to find the derivative of y. And I don't know how to differentiate x to the x. So I'm performing logarithmic differentiation because now I know how to find x times log. Our goal is to find y prime equals. So I want to have this notation of y prime equals blah, blah, blah. Step 3, implicit differentiation. I can even put in the box to see in front of me what are we working with. Here it is. I'm applying derivative to both sides, left and right hand side, using implicit differentiation, keeping in mind that y depends on x. Log of input prime gives you, let me write down, log of y prime equals x to the ln x prime. Let's solve this. What is derivative of log of stuff? 1 over stuff. Make sense? You remember that. You take the stuff inside and you do 1 over stuff. But every time you differentiate something with y prime shows up. Y prime. That comes from the chain rule which we use in implicit differentiation. Because remember, it's 1 over input times derivative of the function inside. But we don't know y prime. That's the whole point. We don't know y prime, so we're looking for it. So we're going to write down y prime. Right-hand side is a product rule. Product rule, PR. Derivative of x is 1. Copy ln x. Derivative of copy x, derivative of log is 1 over x. And because x is independent variable, we just leave it as 1 over x. You can think about 1 over x times derivative of the function inside. But the function inside is x, so it's times 1. So actual logic makes sense here. And we just don't write it down. X cancels out with 1 over x, which actually, it's a good question if we can do it. X is not 0, so yes, we can do it. We can cancel out only stuff which is not 0. Now, step, let me show you my steps again. We're doing implicit differentiation. Differentiate both sides. And you are gonna get this picture, y prime over y. Did we get it? Stare at your notes. Do we have y prime over y? That will be always the same. Why? Because ln of y gives you 1 over y times y prime. Solve for y prime, have the answer. So step 4. Step 4 is not anything new. We're performing implicit differentiation, so you know how to proceed. Identify y prime, isolate it. Y prime equals, well, the only thing I need to get rid of is 1 over y. So I'm going to multiply by y. It's going to be ln x plus 1. Don't forget, x over x is not 0, it's 1. Times y, different color, times y. That is the answer, but we don't like it because it has x and y. But we usually had that before. With implicit differentiation, we had x and y in the answer. But this time we don't have to. Do you know why? Think about it and tell me. What can be better in the answer?
You just replace y with x to the x.
Exactly. Let me repeat. We have y. It was given explicitly this time. So why not to write it down? Answer. Plug in y. Y was given right away. In our case, it's x to the x or whatever it is. And the answer follows y prime equals or dy over dx ln x plus 1 times x to the x. And I actually don't want to distribute, and it does look better if you don't distribute. X to the x. That is the answer. That's your homework problems, and they always put the problem like this on the test, usually as a free response question, because it requires steps, so we grade this as a free response question. Yes?
So couldn't you just rewrite the original function as e to the ln of x times x? And then take advantage of that?
I will show people right now. That's a very good comment. Very good comment. Let me do it in a second. Questions? What do you think? Let me show you your homework. Look at this. You have number 26. Do you see x to the minus 7 cosine? You do exactly the same thing. You do. Oh, someone did it already. Good job. You do exactly the same thing. ln to both sides. You have this y prime of 1 over y. Multiply, distribute to get the answer. And x to the 2x. That's usually what they put in a test, is x to the some kind of x. It's x to the 5x. It's easy to grade. And we show it in the class, and so on. So the last two problems, in my opinion, is not enough to practice. But this goes to the exam. I can really tell you. I don't even have exam in front of me yet. They did not send it to me. But I can tell you, logarithmic differentiation always goes to the exam. And because it has steps, it's a free response question. So it's going to be expensive. Questions and comments, and I'll show you the smart thing you mentioned. There was a very smart comment here. So this is one example only. I mean, you can learn to do it faster than what I did. I was explaining all steps, but technically speaking, this is one example. How to differentiate x to the x. So the goal was find derivative of y, which was input to the input function. And we did, we found it. Y prime is, no wonder log is involved into this case. Log, it's copied itself. So how fast is exponential function? It's as fast as itself. That's why no wonder x to the x show up, because it is kind of exponential function, but just not. So I'm not surprised that this part showed up, that's how fast it is. Times, log is involved, because it's some exponential and stuff, plus 1. Very interesting. And now there was a question. Note, for the very first step, step 1, when I applied log to both sides, it was ln y equals ln x to the x. Ln x to the x. Instead of that, someone just mentioned, we don't have to do that. We can actually use definition or use definition or even inverse log. I'll just show it to you. Y equals. Actually, let me ask you, do you think it will work or not? Which one did you offer?
E to the ln of x.
E to the ln of x to the x. What do you think? Will it work?
So this is just giving y is equal to x to the x.
Well, let's see. Let's see if it's going to work. So e to the, first of all, it is legal because e to the ln of stuff, let's call it u, is u. So that's legal. You can actually always do that, even with 1 or whatever you want. E to the ln 1 is 1, so. And now we're using the same property as we did before. This tiny x is going to go down, and we are going to have y equals e to the x, ln of x. Now we have that. X is times. And now you find derivative of that. Can you? So the goal is to find derivative. Again, goal. So step 1, we did definition instead. Step 2, we used property of log to push down the power. That's why we're using it. Goal, find y prime. Can you? Is it possible to find y prime now? What do you think?
Yes.
Yes. It's e to the stuff. Let's try. Step 3. Y prime equals derivative of e ln x prime. Derivative of that. Which is, first of all, I see that this is some kind of u. So I'm working with e to the u. E to the u prime gives me e to the u. Well, let me actually tell you. E to the u prime is copy times u prime. That's chain rule. So that's what I'm going to do. E to the u is e to the x ln x. I'm just copying it times derivative of the function inside of the exp. And that's derivative of x ln x. But that's product rule. Product rule. 1 times ln x plus x times 1 over x. We did it already. It's the same product rule we had before in the same example. Like so. And that is the answer. That is the answer of the problem. Is it the same as the answer we got before? Let me zoom out. Here it is. Y prime in the red box and y prime we just got. Is it the same?
Yeah.
It is. Let me show you. It's like magic of logarithm and exponential function collaborating together. Step 4, answer. Answer. Y prime equals e to the x times ln x. If I put this x back on top of it, because why not? Then I will have e to the ln x to the x, and I can undo it with ln. Then I'm going to simplify the result of the product rule. ln x plus 1 cancel out. Y prime equals x to the x, ln x plus 1, and the answer is the same. And actually, you don't have to do this step with e and whatever. Nobody will require to do this step. You can leave it as e to the x ln x. That's fine. But it looks nicer than x to the x is there included in the answer. Yeah?
How come for the first solving it, you made y to the ln to
Y to the ln, oh.
for the first method?
For the first method, right?
Yeah, you did that with the simple you didn't make y to the power.
Yeah, that's the whole point. Very interesting. It's the same idea, but using two different beginnings. The beginning one, the way I like to teach, because people usually don't mess up with this one, is apply log to the left-hand side and the right-hand side as a bomb. You just threw it, and then everything now is inside of log. The method 2, which we just realized, is just the beginning of the same method. Don't touch y. Keep it y equals. And instead, rewrite the right-hand side. Oh, go back. X to the x was rewritten as e to the ln of x to the x. And that is legal. You can write down like this. Some people do it often when they feel it is, give them some convenience with calculations. So you can do this way too. Did it? I don't think it answered your question though. I just realized.
Yeah, that makes sense.
Oh, you did? I did? Oh, okay. I'm glad. I just like talking to myself. Like, did I even answer your question? I'm glad I did. So this, do you know how to call this idea? Basically, you're using definition, and you're using the fact that those two are inverse functions. Inverse functions. Basically, what we did is y equals 8 can be written as y equals e ln 8. That's what we did. You can do that. So very good. Choose the one you like. I don't mind. Does that make sense? So this is not very easy. I have lots of steps. That's why I decided to dedicate time today. This homework is due tonight. Don't forget. It was extended by 2 days already. Did you finish it by Monday night? You should have. But if not, do it by tonight. logarithmic differentiation for you. I have examples, I have videos on some of your homework examples. I think I have solved x to the sine for you in my videos. X to the cosine, I think I solved it. So practice this, especially exam 2 is coming exactly in 2 weeks on Monday, but not next Monday, the other Monday. That's good. Let's move on with more derivatives. Actually, I can probably show it here. More derivatives. Let me see.